Thank you, Hussein. So, hi, I'm Kean Mariotti. I am a software engineer at CSCS. And in the last few years, I was involved in container technologies at CSCS. And today I will present you Sarus, which is the OCI-compliant container runtime that we developed. So first, I will give you a quick introduction on containers and on the experience that we gathered at CSCS in the last few years working with them. Then I will present you what we found to be the CSCS requirements on containers, what we expect from an ideal container runtime in order to be suitable for us. Then I will go through an evaluation of existing solutions for containers, so that at the end of that evaluation, it will be clear why eventually we decided to develop yet another container runtime. Then I will present you Sarus and some details of its implementation, and eventually I will show you a couple of examples of Sarus in action. So first of all, just a curiosity, how many of you are already familiar with containers and know how containers work? All right. So I prepared a very quick and dirty explanation about containers, so hopefully it will be enough. You can think about a container as, first of all, you have an image where you package the application that you want to run, as well as its dependencies, software dependencies. Oh. Or maybe there is some. No, microphone's on. But maybe I can raise the, okay. Well, I will just talk louder then. So you have this, sorry. So, can you hear me now? Yeah. Better? Okay, cool. Yeah, I can also hear it's better. So you can think about this image that contains the application that you want to run, as well as the software dependencies. For example, they could be other executable binaries or libraries. Then you can take this image and you can execute that application on any machine that has a container runtime that can be used to create the container from the image. So the advantage is that creating that image is easy and it is portable. You can run it on any machine with a container runtime. And I will show you can also get, basically there will be no performance loss when you run the application inside that image. So the picture on the slides show the differences between the more old-fashioned hypervisor and virtual machine approach versus containers. So when you use an hypervisor, you have the host operating system, then on top of it you run the hypervisor as an application, and inside the hypervisor you run yet another operating system, the guest operating system, and on top of it eventually you run the application that you want to run. If you look on the right, you can see how a container works. Basically you have the host operating system. On top of it, you use a container runtime, for example, Docker, which is used to instantiate the container and execute the application inside the container. And the advantage is that the Docker engine is only used to create the container. Then at execution, the application is basically running on the host operating system without anything in the middle that eats performance. So there are already quite a few container technologies out there. Some of them are also HPC focused, like Singularity, Charlie Cloud, and Shifter. And I will show an evaluation of some of these technologies later. So this is the experience that we got at CSCS working with containers. We started in 2015 doing some early Docker evaluation for accessing GPUs from Docker containers. Then in 2016, we decided to try to use Shifter. So we invested some time extending Shifter in order to access GPUs and the native MPI from the container. In 2017, we finally deployed the Shifter into production at CSCS. And in 2018, we developed an extension of Shifter, which we called Shifter NG, which stands for Next Generation. So basically, Shifter NG had a couple of extensions, which were a Docker-like command line interface, as well as a new component that we called the Image Manager. And the Image Manager was used by the user to easily pull images from the cloud or load images from a tar file, list available images to the user, and remove images. And in 2018, we rolled out this Shifter NG into production. And now, in 2019, we finished the development of the new container runtime, which is Sarus. So gathering all the positive and negative experience that we had with containers in the last few years, we came up with a list of requirements, a list of expectations that we have from a container runtime in order to be suitable for us. So the first requirement, of course, is suitability for HPC. The container runtime should work with diskless nodes. It has to be compatible with the workload manager. It has to work nicely with the parallel file system. And of course, it has to prevent any form of privilege escalation, because on the HPC system, we have multiple users. Then another very important requirement is pluggable vendor support. So our idea is that the vendors like NVIDIA or Cray, they should provide their own plugins that we can add to Sarus in order to enable access to hardware like GPUs or the high-speed interconnect. So here the idea is that that burden would shift from the HPC side to the vendor. And in order to do that, we need a plugin interface, a standard plugin interface. And right now there is an ongoing effort in the HPC world, in the containers world, sorry. And it is called the Open Container Initiative. And this initiative also happens to define an interface for plugins, which is called the OCI Hooks. So we decided that one of the requirements for a container runtime was support for these OCI Hooks. Another requirement is a good user experience. So we wish to have a container runtime with a Docker-like CLI, because users are already very familiar with Docker, and so they would be familiar also with our container runtime. And we also wish to have integration with Docker Hub, because many users are already familiar with Docker Hub, and so shifting to another runtime would be easier. And we would like to have a writable container file system, which means that the user should be able to touch files inside the container. Then we would also like to have a nice administrator experience. For example, easy installation, like installing a single executable binary, or also some way to customize the container, because maybe the system administrator might want to tailor the container to the specific HPC machine, and so it will need to add maybe some plugin or something to modify the container. And last but not least, we want to have a low maintenance effort. For example, with a small code base, which could be achievable reusing third-party software, or leveraging community efforts. For example, having a large community that takes care of extending the application and fixing bugs and vulnerabilities, etc., etc. So before we decided to develop a new container runtime, we tried to use something that was already available. So we took into account a few already available container technologies, and we evaluated them based on the 5 criteria that I just explained. So in this table, you can see a summary of the evaluation that we did. you can see that we evaluated 6 of the main container technologies, and I will just try to quickly summarize the results of this evaluation. So if you look at Docker, for example, you can see that it provides a very good user experience. Actually, it provides the user experience that we are targeting. However, it is not very suitable for HPC because it has problems like it is not compatible with the workload manager, and it doesn't provide any plugin interface at all. And that was an important point for us to have this pluggable vendor support. Then if you look at Singularity, Singularity is designed for HPC. However, it doesn't provide the OCI Hooks interface, and it also doesn't provide the user experience, exactly the user experience that we wanted. Then Charlie Cloud was also designed for HPC, but it doesn't provide any plugin interface at all, which for us was a big minus. Then we have Shifter, which was also designed for HPC. However, it doesn't provide the OCI hook interface, and in our experience, it was also hard to maintain, both for system administrators as well as for developers. Then we also considered LXC. However, LXC was not suitable for HPC because it is rather focused on VM-like containers, which is not containers that only execute an application, however, containers that also execute all the processes, all the services that you usually find in a Linux environment, starting from the init service, and which then branches into the other ones. And finally, we evaluated RunC. So RunC as it is not designed to be used in HPC. However, it provides the OCI hook interface, which is exactly what we wanted. And it also provides a very good administrator experience because it is a single standalone binary. So unfortunately, if you look at this table, you will see that we couldn't find any existing technology that was 100% suitable for us. So that's why we decided to develop yet another one, which is Sarus. So Sarus is suitable for HPC. For example, internally Sarus takes the container image and then it compresses it into a squashfs file, which is then stored on the parallel file system. And running containers out of a single and relatively large file, it's very friendly for the parallel file system. Then Sarus is compatible with the workload manager, and Sarus also provides native GPU support and native MPI support. So Sarus has the OCI Hooks interface that we wanted. It is partially implemented through RunC because we decided to use RunC as one of the internal components of Sarus. And we already have native GPU support through the NVIDIA Container Runtime hook. I will talk about it later. So Sarus provides the user experience that we wanted, which is Docker-like command line interface and the integration with the Docker Hub and the writable container file system through OverlayFS. Sarus also provides a decent administrator experience because it is a single executable binary. It provides the OCI hooks, which could be used to tailor the container to the HPC system. And it provides a secure container isolation through RunC, which is a large community, and we rely on that community to quickly find vulnerabilities, if any, and to quickly patch them. And last but not least, we have a relatively low maintenance effort, I would say. Sarus has a quite small code base because internally we reuse RunC, and we also reuse other libraries and third-party software, which means less code for us to be maintained. Sarus is compliant with standards, and it is a well-tested code base. Right now we have a 94% coverage of unit tests, which is quite good, I would say, especially if you consider that the error handling code is usually not tested in the unit test. So the actual production code is more covered than 84%. Moreover, we also have quite a few system and acceptance tests. So this is an overview of the Sarus architecture. We have Sarus, which reads configurations from a JSON file. Then Sarus can read images, either from the cloud, for example, from Docker Hub, or from a tar file. And those images are then stored into the parallel file system. Then when we want to run an image, Sarus internally uses an OCI runtime, which is currently run C. So this is an example of what happens inside Sarus when we insert an image into the system. So the users interact through the CLI with Sarus. Then the CLI instantiates the image manager component. The image manager component reads configurations from the JSON file. For example, he needs to know where he has to store images in the parallel file system. Then the image manager can read the image either from Docker Hub or from a tar file. And that image is then compressed into a SquashFS file and stored into the parallel file system. So here we can see what happens inside Sarus when we run an image. So the user always interacts with Sarus through the CLI. Then the CLI uses the image manager to query the parallel file system and to get information about the image that we want to deploy. And then we also need some information from the configuration of Sarus, which is from the JSON file. So those three pieces of information, configuration from the JSON, command line parameters, and the image information from the image manager, those three pieces of information, they are merged in order to create the OCI bundle. The OCI bundle is what is expected by an OCI-compliant runtime in order to execute the container. And long story short, the OCI bundle is a directory which contains the rootfs of the container, as well as a configuration file, config.json, which is used to configure the OCI-compliant runtime. So eventually, Sarus passes the ball to the OCI runtime, for example, run C, passing the OCI bundle to it. And the OCI runtime executes the OCI hooks that it was configured to execute. For example, the MPI hook to bring the MPI drivers into the container, the NVIDIA hook to bring the NVIDIA drivers into the container, plus other hooks. Eventually, when the container root file system is ready, the OCI runtime executes the containerized process. So this is a list of hooks that we are using at CSCS. As you can see, we are already using quite a few of them. Actually, we are really striving to use hooks instead of further extending Sarus. We want to keep the Sarus code base as small as possible and easy to maintain, and then we just plug in additional logic through the hooks. So one hook that we use is the NVIDIA Container Runtime hook in order to enable GPU support. And here I would like to point out that this hook comes from the NVIDIA GitHub page. And basically, we download that hook from the NVIDIA GitHub page, and then we take it exactly as it is, and we plug it into Sarus, and then we transparently get GPU support. We don't have to do anything else than that. So this is an example. This clearly shows that designing Sarus with the OCI hooks support was a winning choice. It is already paying off. Then we have the MPI hook, which was developed by CSCS, and it enables the container to access the Cray MPI. So at the moment we develop this hook and we are maintaining this hook. However, ideally we would like that one day Cray will take care of it and Cray will provide its own OCI hook. Then we have the SSH hook, also developed at CSCS, and this hook allows to SSH into a Sarus container. Then we have the SLARM synchronization hook. Basically, this hook is a synchronization barrier. It makes sure that all the containers have been created, also across multiple nodes, before any application is executed inside the container. There are some use cases that require this kind of synchronization. And finally, we have the timestamp hook, also developed at CSCS, and this is a developer tool that we use to time and profile the execution time of the hooks. So this is what the Sarus command line interface looks like. We have the command Sarus pull to pull images, for example, from Docker Hub. Then we have the command Sarus load to load images from a tar file. Then we do Sarus images to list the available images of a user. We do Sarus RMI to remove an image. And we do Sarus run to create a container and run an application inside the container. So these are the corresponding Docker commands. As you can see, the Sarus interface is highly consistent with Docker. The commands look pretty much the same. So, and this is an example of Sarus in action. In this case, we were running TensorFlow with Horovod. We ran two versions of this software, a native one and a containerized one. We built a container with it. And we ran the test on multiple nodes. So the two lines, red and blue, show the performance of the two versions. And as you can see, container and the native version are performing basically the same. Actually, in this case, starting from 32 nodes, you can see that the container was performing slightly better. So this is another example of an application that we containerized, COSMO. COSMO is used in Switzerland by Meteo Suisse. They use it to compute the weather forecast. So we ran two configurations of COSMO. One was, so first of all, this was a weak scaling test. And we ran two configurations of it. So one was a 160 times 160 grid, horizontal grid per node, and the other one was a 256 times 256 horizontal grid per node. So the top two lines, red and blue, show the performance of the native version versus the containerized version of COSMO with the 256 times 256 setup. And as you can see, they are basically the same. And the bottom two lines, they show the performance of native versus container with the 160 times 160 setup. Again, performance is basically the same. All right. So thank you for your attention. This was Sarus. And if you have any questions, please feel free to ask.